Okay, good afternoon. In this video, we're looking at exercise 14E, which is symmetry in the unit circle. The two key concepts we're going to cover are what the values of sine, cos, and tan are in the four different quadrants of your unit circle in terms of their signs. So whether they're going to be a positive value or a negative value in these four quadrants. And the other key concept is the symmetry properties of our unit circle. Understanding that our unit circle is symmetrical allows us to find values in quadrant 1 and link it to identical values in other quadrants. Okay, so here's what we've done so far with our unit circle. With our unit circle, we've been able to calculate the values of the sine and cosine at the following angles. So I'll label it here. Nothing for you to copy down as notes yet, but we've got 0 degrees, 90, 180, and 270, and 360. And the corresponding radian measures are 2 pi, pi on 2, pi, and 3 pi on 2. Understanding that our sine is our y-coordinate of the point on our unit circle. So let's bring it to 30 degrees in our example. Okay, so here's our point at 30 degrees. Our sine, is our y-coordinate, and our cosine is our x-coordinate. And what you notice, as we increase our angle, the values of our sine and cosine change. Our sine reaches a maximum value of 1 at 90 degrees, and our cosine becomes 0. Now, as we increase our angle to the other side, we notice that the sine decreases to 0 and the cosine becomes -1. It becomes -1 because our x-coordinate here is -1. So that's what we covered in 14b, and in 14c we covered the fact that the tangent is related to the gradient. So in quadrant 2, the gradient was in the downwards direction, which is negative. When our point is at 90 degrees, up there, we have a vertical line, which implies that our gradient is undefined. And when we are at 180 degrees, then we have a 0 gradient because we have a horizontal line. Okay, so that's what we've covered so far. Now, what we're going to do first is to see some symmetry properties in our unit circle. I'm going to bring our point back to 30 degrees. 30 degrees here. And we notice for a fact that at this point sine at 30 degrees is 0.5. Okay, turns out to be exactly 0.5. Back before calculators were made, people would actually draw a unit circle of radius 1, and then they'd measure an angle of 30 degrees, and then they'd take their ruler and measure the height to this point. And the height of this point would be defined as 0.5. Okay, so the sine of 30 degrees is 0.5. The cosine of 30 degrees is 0.866. Once again, someone took a ruler and measured it. Right, so let's see where this coordinate appears in other parts of the quadrant. So as I keep going to the other parts of the quadrant, notice when sine of 30 degrees becomes 0.5 again. So look at that value up there. That corresponds to the height of this triangle. And you can see that it becomes 0.5 right about here. Right about here, where the angle is 150 degrees, sine of 150 is equal to 0.5. Notice that the sines there are vertical lengths, they're equal to the same value. But the cosine of 150 degrees, it would be negative 0.866. Now if you compare the cosines at these angles, at 30 degrees it was positive, and at 150 degrees it was negative. So what's actually going on? Keep in mind that we're always measuring angles from the x-axis. So point P here We reach that by going up 30 degrees. But in the other direction, because of symmetry, we can consider this as going backwards by 30 degrees. If we go from 30 degrees from the positive x-axis, we also get the same value if we go backwards by 30 degrees from the other side of the x-axis. But some things remain the same, like the sine, they're both 0.5, but the cosine, they switch signs. Also the tangent as well. Initially in quadrant 1, our tangent was positive. In quadrant 2, our tangent is negative. So that's a bit of an introduction to the symmetry in a unit circle. So at this point, we're going to take down some notes. If you've got your book ready, please copy down the title, 14E, and we'll take some notes down first. So we start with the fact that on a unit circle, let's draw a unit circle. On a unit circle, we always measure angles from the positive direction of the x-axis. Angles always go in this direction. Okay, that's a very key point. Now, at this point, we come to the fact that in other quadrants, in quadrant 2, there are values of sine and cosine that correspond to angles in quadrant 1. So here are the following notes that we're going to copy down. In quadrant 1, and quadrant 1 is where our angle sits between 0 and 90 degrees. In fact, we'll maintain our usage of radians here, so it's 0 to pi on 2. Little unit circle, y, x. Then when we go to a point on our unit circle, the point which has coordinates x, y, x is represented by the cosine and y is represented by the sine. So let's write this down. In quadrant 1, sine of our angle is x, and cosine of our angle is other way around, my mistake. So sine is y. Sine is y because that's our vertical part up to the coordinate p, and cosine is x because that's the horizontal component, the x coordinate. Now our tangent, our tan theta, is sine over cosine, so it's y over x. Now at this point, note that all of these values for sine, cos and tan, the x value, the y value, and the gradient, they're all positive. They're all positive because we're sitting in the first quadrant where all values are positive. So all positive. Okay, here's what I'm going to ask you to do next. Label the angle that we went to point P, and then we're going to copy and paste this diagram down here to represent what happens in quadrant 2. In quadrant 2, and quadrant 2 exists where our angle is between pi on 2 to theta to pi. So this is in quadrant 2 because pi is 180, pi on 2 is 90 degrees. We're going to make a unit circle with y and x. We're going to go up to point P with this angle, but we're also going to make another point on the other side of our unit circle. The idea is to make these symmetrical from the x-axis. So if we went to point P using angle theta on one side, we would go to our other point using negative theta on the other side. Now this location would be pi, on our unit circle. And keep in mind that we're measuring angles from the x-axis. So to get to this location, then what we would do is to go 1 pi radians across, so half a circle across, then an angle theta backwards. Now this angle up here would be pi minus theta. So in other words, the corresponding angle to theta in quadrant 1 would be pi minus theta in quadrant 2. These two angles would make symmetry. Now let's consider what happens. In quadrant 2, notice that our point, let's call this point Q, give it a different letter. If point P was x, y, point Q would have the coordinates. Well, the y coordinate would be positive, but the x coordinate would be negative. So it would be negative x, comma y. That's point Q. And that tells something to us about the value of the cosine. Cosine, remembering, is our x coordinate, which means in quadrant 2, our x coordinate is negative. Our direction for the cosine is pointing in the negative direction. So let's summarize this. In quadrant 2, sine of pi minus theta implying that we're in quadrant 2 now. We're 1 halfway across, then a bit of an angle back. That would be equal to the coordinate y. Now, our coordinate y is the same as the coordinate y in quadrant 1. They're both sitting facing in the same direction, which is upwards. So that would make sine of pi minus theta equal to sine of theta. They're both still positive. Now it changes a bit for cosine. Cosine of pi minus theta is equal to negative x. So that means cosine of pi minus theta would be equal to negative cosine of theta, because we've defined x to be cosine of theta. Okay, so two key facts that we've learnt. The values of sine and cosine link up with quadrant 2 to quadrant 1. In quadrant 2, sine would still be positive, as they would be in quadrant 1, but cosine would be negative, the negative value of what the value was in quadrant 1. Now lastly, we can look at the tangent. The tangent in quadrant 2, the tangent in quadrant 2, it seems to be negative, it seems to be going down. But we can prove that because we can do rise over run. So our rise from here to here, our rise would be negative y. Our run would be from here to here, which would be x. Now using the gradient is one way to do it. We can also use the fact that that our tangent is sine over cosine. So sine over cosine, which is y over negative x, but they both turn out to be the same thing. And that would be negative tan theta. Keep in mind, tan theta is defined by sine over cosine y over x. So if we have negative y over x, that would be negative tan theta. In other words, the value of the gradient would be the same, the steepness is the same, but they're going in opposite directions. Okay, that's the third key fact. So this is what we get in quadrant 2. Now at this point, I think it's important for us to see how these formulas help us with solving problems. So I'm going to turn off the projector now, and I'll place question 1 up on the board. So here is question 1. Give me a moment to pull it up. Okay. Question 1. We haven't finished our other quadrants yet, so you'll need to leave a bit of space for the other quadrants. So in example 1, if sine of x is equal to 0.6, find sine of, that would be sine of pi minus x. Okay, so let's have a think about this. In this question, they say that for a certain angle, x, the sine of that angle is 0.6. Now, if you want to draw a little diagram to represent this, that diagram would look like the following. Okay, so for some value of x, this isn't our x coordinate anymore, this is an angle because the x is sitting with the ratio. So for some value of x, our sine, or the height of this triangle, is 0.6. Now they're asking for what the sine would be if it was in quadrant 2. So in quadrant 2, pi minus x, that implies that we go pi units across, then x backwards. So we're at this point up here. And what is the sine of that point, or the height of that, or the y coordinate? You can tell by symmetry that they should be both 0.6. Well, let's prove that mathematically. Okay, find sine of theta minus pi minus x. Important to note that this must be in quadrant 2. So, in quadrant 2, we know for a fact that sine of an angle, we'll start with quadrant 2 first. So sine of pi minus whatever angle we have should be equal to sine of our angle. So this line is something we've shown earlier. This line is what we showed here because we knew that the height up in quadrant 1 is the same height up in quadrant 2. Okay, now in this case, we know that sine of pi minus x is equal to sine of x. All I've done is I've replaced theta with x, because theta can stand for any x value, but theta can stand for any angle, but x is a particular angle. Okay, now let's think. Sine of pi minus x is equal to sine of x. And they've given us what sine of x is. Sine of x is 0.6. So that would be equal to 0.6. And we've answered our question now. Sine of pi minus x would be equal to 0.6. That's exactly what we saw earlier when we looked at this diagram. Now let's do a similar example. Question 2. If cos x is equal to let's call this 0.4, find cos of pi minus x. Okay, we can use the same diagram as before to describe it, but this time we're looking at the horizontal part instead of the vertical part because cosine stands for the x coordinate. So let's try and figure this out. Once again, we need to identify that this is in quadrant 2. And in quadrant 2, we know that cos of pi minus theta, that's equal to negative cos of theta. Okay, and we found that earlier because comparing quadrant 2 and quadrant 1, if quadrant 1 has a positive x coordinate, quadrant 2 implies that we have a negative x coordinate. So at this point, what we can do is we can write, okay, cos of pi minus x is equal to negative cos of x. And we know cos of x is equal to 0.4, so it's negative 0.4. And at this point, we've answered our question. Find what the cosine in quadrant 2 would be, and the cosine of quadrant 2 would be negative 0.4. The implication is that if we've gone an angle x, and our cosine was 0.4 in quadrant 1, in quadrant 2 we should be negative 0.4. Okay, so there are examples 1 and 2, and we're going to put them aside for a moment because we've just seen how we use these formulas to help us calculate the sine, cos and tan in other locations of our unit circle. Okay, now we're going to do quadrant 3 and quadrant 4 now. So we'll go back to our notes. In quadrant 3, our angle will sit between pi and 3 pi on 2. Okay, our angle sits between these, where pi is 180 and 3 pi on 2 is 270 degrees. We'll make another little unit circle. Okay, y is up there, x is here. We'll make another point up to point P, x, y. And then we see what happens when we measure a symmetrical angle in quadrant 3. Now, our point in quadrant 1, remember, we measured it from our x-axis. So to measure an angle in quadrant 3 from our x-axis, we've got to start on the pi side of it. Okay, and what will happen is we'll join a line down here. We'll call it Q. And Q is found symmetrically by going the same angle in the forwards direction from pi. So the angle to point Q, which is symmetrical to P, that would be located at pi plus theta. So pi plus theta is how you get to point Q, because you go pi units across, then another theta to our point of interest. Compare that with pi minus theta. Pi minus theta gets us to quadrant 2. Pi plus theta gets us to quadrant 3. Okay, now what are the coordinates of point Q down here? Well, the x and y coordinates, they're both negative. X is negative in this direction because we're going in the negative direction, and y is also negative. So this is negative x and negative y, which implies that the cosine in quadrant 3 is the negative value of the cosine in quadrant 1, and the sine value in quadrant 3 is the negative sine value of quadrant 1. So let's summarize this. We'll start with sine first. Sine in quadrant 3 is equal to negative sine of, give ourselves a bit more room, negative sine of quadrant 1. And the cosine in quadrant 3 is equal to the negative cosine of quadrant 1. Now lastly, the tangent. The tangent in quadrant 3, well, that's equal to sine over cosine. Well, if we do sine over cosine, well, negative sine over negative cosine, these negative signs will cancel out, and sine over cosine would just be equal to the tangent. In other words, the gradient in quadrant 3 will be equal to the gradient in quadrant 1, and you can see how that's a straight line. Okay, so we've got these identities for quadrant 3. Now we're going to finish up with quadrant 4. And our angles in quadrant 4 are from 3 pi on 2, and it goes to 2 pi. And once again, we'll do one last unit circle. X, y. Okay. Once again, we're linking it to quadrant 1. And our angle is from our x-axis. It goes up there. In quadrant 4, we're down here. But remember, our angles are always measured from the x-axis. So going the same angle but in reverse, we would end up somewhere down here. This would be an angle negative theta, and that goes in the clockwise direction. Now at this point, point Q, we notice that, before we do that, we should mention what this angle would be. So this angle is obtained from going a full revolution, 2 pi around, then going a theta angle backwards. So this location here would be the angle 2 pi minus theta. 2 pi minus theta, one full revolution, then an angle theta back. Now, point Q there, the x and the y coordinates. Okay, let's start with x. X is still positive because point Q is in the positive region of x. But the y value is negative because it's down there in the negative region of y. And that will give us enough information of linking the sine and cosine to those in the first quadrant. Okay, let's do sine. The sine in the fourth quadrant, 2 pi minus theta. So 2 pi minus theta, knowing for a fact that sine becomes negative in quadrant 4, it would be the negative value of the sine in quadrant 1. Now for the cosine, that cosine is still positive. It's a positive x coordinate. And the tangent, okay, notice for a fact that if we do sine over cosine, well, it's negative sine over positive cosine, and a negative divided by a positive becomes a negative. And sine over cosine is tangent. So this is what we get, and these are all the different symmetry properties that we get when we look at the different quadrants in quadrants 2, 3, and 4. So that means, if I give you an angle, and then you can identify the quadrant from that angle, you can tell me whether sine is positive or negative, cos is positive or negative, and tan is positive or negative. So here's an example. If we were at an angle 3 pi on 4, now 3 pi on 4 is between here and here. Here's half of pi, here's 1 full pi, so 3 pi on 4 is in quadrant 2. Then sine of 3 pi on 4 would be positive. Sine of 3 pi on 4 would be positive. And the reason that it's positive is because the y coordinate is positive. The cosine of 3 pi on 4 would be negative. Cosine of quadrant 2 would be its negative value of quadrant 1. And that's because the x coordinate is pointing in the negative direction. And lastly, the tangent would also be negative. The tangent at 3 pi on 4 is negative because it's facing downwards. Okay, now there's a way to summarize all of these together, and this is to use the rule. So the rule is going from quadrant 1, 2, 3, and 4, we can label it A, S, T, C. A stands for all trig ratios are positive. In quadrant 1, all of sine, cos, and tan are positive. The second quadrant S means that only sine is positive, all others are negative. T stands for only tan is positive in quadrant 3, and C stands for only cos is positive in quadrant 4. Only cos is positive here. So drawing this on your test or your exam right at the beginning helps you remember which of the ratios are positive or negative. Now there's a few ways you can remember this. One way is all stations to Caulfield, where the starting letters correspond to the different letters you put on unit circle, and there's other ways of remembering this as well. Now there's one more symmetry property that you need to know, and this is what happens when we go backwards in an angle. So here's point P, x, y, and I'm going to label this negative angles. So this is going to be a bit separate from all the others, but we're still dealing with symmetry. This has got to do with negative angles. Now keep in mind that our angles should be measured from the x-intercept, positive x-intercept, in the anti-clockwise direction. But if we go in the clockwise direction, this is what happens. If we go clockwise in the same direction, negative theta, then what we get is point Q, where the coordinates would be x, positive x, because x is still positive, pointing in the direction to the right, and negative y. So that implies that if we have a negative angle compared to a positive angle, what changes is our sign. Our sign becomes the negative of its value in quadrant 1. The cosine doesn't change, but the tangent obviously would change because that's sine over cosine. Okay, so let's summarize this. Sine of negative theta, that would be equal to, okay, negative theta because we're going backwards in angle, that would be equal to negative sine of positive theta. By symmetry, if in quadrant 4 we're going downwards, in quadrant 1 it should be its negative. For cosine, and negative theta implies still its positive value because the cosine doesn't change, we're still pointing towards the right. And the tangent, the tan of theta, that's going to be equal to its negative value. Negative sine over cos would be negative tan. Oops. I forgot to add it a bit here. So tan of the negative angle would be negative tan of its positive angle. Now, here's how you use it. In a similar vein as before, like all the other examples, forget about those birds. If sine of negative x is equal to, let's say, 0.8, find sine of x. Okay, we're going backwards by a certain amount of angle. What angle would that be equivalent to if we were going forwards? So to answer this question, what we notice is sine of negative x, and negative angle implies that our sign becomes negative. That was from the symmetry property we discovered earlier. So to answer this question, you'd write, okay, sine of negative theta, because theta is the general angle we have, that has to be equal to negative sine of positive theta. Now in terms of our example, for our particular value x, sine of negative x is equal to negative sine of x. And our particular value of negative x, okay, that negative x there, that was 0.8. So we sum it into the left side, 0.8 is equal to negative sine of x. And then to find our value of sine x, we just bring the negative to the other side. So therefore, running out of space, sine of x is equal to negative 0.8. So let's consider what that means. We've gone an angle backwards by a certain amount, and it's gotten us to a 0.8 value of sine. So let's in fact describe that visually. Okay, so we're going by a certain value x in the backwards direction, and it's given us a sine of 0.8. Okay. Now the equivalent value of x that we get if we were traveling forwards, okay, if we were traveling forwards by the same amount, have a look at what this angle would be. We've gone half a revolution plus a bit more, so backwards we should also go half a revolution plus a bit more. So half a revolution plus a bit more, that would be the same value as this same amount of angle as what we had backwards, but going forwards that would be positive x instead of negative x. So at this point, what would be our sign? That's the question, find sine of positive x. And we notice that by symmetry it'll be negative 0.8. Mathematically we know it's negative 0.8 because of symmetry. If you go backwards by a certain amount of angle, that's the same as going forwards, but your value would be negative for sine. For the others for cos would be the same, they would be both positive, and for tan would turn it into its negative value. Okay, so we're going to finish up by doing a few more examples. We're done with the notes now, and these are the following examples. So we've done question 2. You can consider this like question 2.5. Question 3. With question 3, if sine of x is equal to 0.6, find a sine of, that would be pi plus x. Okay, find this. Now with this example, we're not looking at negative angles, we're looking at angles in other quadrants. I can tell because pi plus x indicates that we're looking at quadrant 3. Okay, so you'd either note this on your test question or you'd have this in mind. Now the relationship that links quadrant 3 sine to quadrant 1 sine is like this. Okay, so sine of pi plus theta, where theta is a general angle. In quadrant 3, we know that only tangent is positive, which implies sine must be negative in quadrant 3. In quadrant 3, that would mean sine is negative. So now what we can do is we can apply our question and figure out what sine of pi plus x is. So let's figure this out. Therefore, sine of pi plus x, where x is our specific angle, that would be equal to negative sine of x. Working on, we know that sine of x is 0.6, so that means sine of pi plus x is equal to negative 0.6. And at this point, we've answered our question. Question B, if sine of x is 0.6, find sine of 2 pi minus x. Same thing, in this case I know that 2 pi minus x is in quadrant 4, and in quadrant 4 I can tell sine is negative as well. It's negative because only cosine is positive in quadrant 4. So here's what I write down. Sine of 2 pi minus theta, that's our quadrant 4 angle, is equal to negative sine of theta. So applying it with our question for that specific x value, that means sine is 2 pi minus x, and that's equal to negative sine of x. At this point, we can answer our question. Sine of x is 0.6, therefore in quadrant 4, our sign becomes its negative 0.6. Okay, a few more examples. This time we'll do them a bit more quickly. Here's question 4. We might need a bit of space for question 4. For question 4, we need to find x if sine, let me make sure I've got that question right, if sine x is equal to negative sine of pi on 3. Okay, and we have x is between pi and 3 pi on 2. So keep in mind that x represents our specific x angle. Now here, I need to first identify which quadrant we're in, because the quadrant tells me whether our sign is positive or negative. Okay, so here we know that we're in quadrant 3. Quadrant 3 because pi is 180, 3 pi on 2 is 270. Now we set up our formula that relates these symmetries for sine in quadrant 3. Okay, in quadrant 3, sine of, quadrant 3, that means we start with pi and then we go a bit of an angle forwards. So that would be pi plus theta. And in quadrant 3, I know that sine is negative. Okay, this is the equation we set up. Now what we're going to do is we're going to sub in our, our information to find what x is. So what we actually have, x, that's on the left-hand side, that's the sum of pi plus theta. Okay, look at those and link them up. Whereas on the right-hand side, pi and 3, that's equal to our theta. So here's what we do. For our specific angle x, we have pi plus theta. Well, theta is given to us. Theta is the pi and 3. In other words, we've gone halfway plus pi and 3 of a way further than pi. And that's equal to negative sine of pi on 3. And notice what we've just found. That pi and 3, negative sine pi and 3, that's the right-hand side. On the left-hand side, we can tell what x is. X is the result of pi plus pi and 3. So therefore, x is pi, pi plus pi and 3. And then the answer is 4 pi on 3. Okay, so let's visualize what's going on. So, what this question's telling us is that if sine is equal to pi plus pi and 3, that means we're in quadrant 3. So we've gone pi and 3 more than pi. Okay, and that tells us that there's a certain value of sine. Sine of pi plus pi and 3. And hopefully you can tell that it's negative because the y value is negative. But that's the same value as what you'd get if you went forwards by pi and 3. So going forwards by pi and 3 will give you sine of pi and 3. And the relationship between these is that one's negative, whereas the other's positive. In other words, sine of pi plus pi and 3 would be equal to negative sine of pi and 3. Same lengths, same vertical lengths, but this is negative. That's saying that when x is 4 pi and 3, sine would be negative of, negative sine would be, when x is 4 pi and 3, that means we're here, then that y-coordinate would be the same y-coordinate as sine of pi and 3, but just flipped around and being negative. Okay. Now that's question 4. Let's do question 5. With question 5, find x if cos x is equal to negative cos 30 degrees, and I think we're in quadrant 2, and 90 degrees. Our specific x value is between 90 and 180. Okay, so let's work this out. First, understand that we're working in quadrant 2. And in quadrant 2, the symmetry equation that links up the cosines are like this. Cos of, quadrant 2 means that we start at pi and we measure a certain angle backwards. Pi, no, not pi, we're working in degree measures now, so 180 degrees. We start at 180, then we go a general angle backwards. Okay, and that would be equal to, now is cosine positive or negative in quadrant 2? Well, cosine would be negative because according to our ASTC, only sine is positive in quadrant 2, which means cosine would be negative. So that would be negative cos of negative cos of our angle in quadrant 1. Now we've set up our general formula. We can start linking it with the information in our question. So in this case, we have cos of 180 minus, in this case, theta. We can tell what the theta is already, but I'll write that down later, is equal to negative cos of theta. So that theta is 30 degrees. Okay, I'll make it a link here. They've given us our theta value. And that theta value exists here as well. So at this point, we can answer the question, because the question is to ask, well, what's the specific angle that we've travelled? Now, the specific angle that we've travelled is 180 minus 30 degrees. So therefore, x is equal to 180 minus 30, and that's equal to 150 degrees. Okay, so we've come to the end of this lesson. We've discovered how the signs of sine, cos, and tan can change in its sign, positive or negative, based on whichever quadrant you're in. And to summarize, the useful mnemonic to remember this is ASTC. ASTC, all stations to Caulfield, and all of those are positive, sines positive, tans positive, and cosines positive, which means all others are negative in the respective regions. Next, we looked at symmetry properties of the unit circle, linking angles in each quadrant. Okay, so that means in other quadrants, at specific angles, you'll see symmetry and the corresponding sines and cosines being equal, but some of them being negative values of the other. We also looked at negative angles. Negative angles meaning that if we go backwards by a certain amount, if we go backwards by the same angle as going forwards, the only thing that changes its sign is the sign ratio, because we're going downwards instead of upwards. Cosine doesn't change because we're still facing in the same direction in relation to right and left, but tangent changes because instead of going upwards and having a positive gradient, we have a negative gradient and going downwards. Lastly, we worked through these examples. Questions 1 and 2 and 3 are related to finding your values of sine, cos, and tan in other quadrants if they give you a particular value in one particular quadrant. Whereas in quadrant 4, you are asked to find the angle when other information is given and which quadrant you're in is given as well. Okay, that's it. I hope that's helped. And your homework would be 14E, questions 1 to 7, all. Okay, that's it. Have a great weekend.